Welcome to Signals and Systems. Throughout this lecture, I'd like to request you to pause this video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In some of the lectures, we'll play around with some of the signal processing ideas in MATLAB. So I'm assuming that you already have some level of exposure to MATLAB. So here's a signal is a set of information that is a function of an independent variable, such as time, frequency, or space. So here's an example of a speech signal. So in the x-axis you have time, in the y-axis you have amplitude of the speech waveform. Note that this signal, also known as a time series or a function, is a variable of time and has an amplitude for any value of time within the range 0 to 0.5 seconds. On the right here is another example of a signal, GDP per capita of a country from 2008 to 2020. Here too the independent variable is time and the dependent variable is GDP. So both of these examples are 1D signal. However, the independent variable does not have to be time, and the signal also doesn't have to be 1D. It could even be, the independent variable could even be a position. In this image here, for example, the independent variable is position. You have x-axis this way and y-axis here to identify the location of each of the image pixel, and each pixel of an image has a certain intensity. So what is a system? A system is an entity that processes a set of signals or inputs to yield another set of signals or outputs. So a system takes some signals and does some operation on that signal and produces an output. So here I'll give some examples of continuous time systems. For instance, in a circuit, a voltage or current signal to the input port can be and voltage current from the output port. So in an electric circuit, often you have voltage or current in an input port, and you take the voltage or current from an output port. So this type of electric circuit is an example of a continuous time system. Our visual system is also an example of a continuous time system. It processes the light inputs and generates action potential or electrical signals to communicate with other neurons in the brain. Glucose metabolism in our bodies is also another example of a continuous time system. So it basically converts glucose and oxygen to carbon dioxide and water and generates the energy that we need to survive. A television set is also another example of a system. So it converts, it takes electromagnetic signals as inputs and generates images and sounds as outputs. So now I'm going to talk about ways you can classify signals. A signal that is specified for a continuum of values of time, or t, is called a continuous time signal. A signal that is specified only at discrete values of t is a discrete time signal. Let's go back to our earlier examples. The speech signal here is a continuous time signal, whereas the GDP data or signal is a discrete time signal. If you compare these two figures, you see that both of these signals' independent variables are time. However, time for a speech signal here is a continuous variable, whereas for GDP it is a discrete variable. In other words, we know what the amplitude of the speech signal is at time, let's say 0.15 seconds, whereas we do not know the GDP value for 2008.5 years. We know between any two real numbers, let's say 1 and 2, there are infinite number of real numbers. So for each value of t, or time, of the continuous time signal, we have one value of the signal amplitude. How then do we store an infinite number of signal amplitudes in a computer for a continuous time signal? Well, Real signals are discretized and then stored in a computer for analysis. So signals in reality are discretized and then stored in a computer for analysis by a process called sampling. The sampling is the process of converting a continuous time signal, such as the one shown in A, to a discrete time signal by taking samples in regular intervals. So the rate at which the samples are taken from the continuous time signal is called the sampling rate, Fs. So if the spacing between two samples in figure B here is capital T, which is also known as the period, then the sampling rate Fs is equal to 1 by T. So the sampling period, that is the time difference between these two samples, is the inverse of the sampling rate Fs here. Okay. So now we can we'll look into another classification of signals, analog and digital signals. So signals can also be classified into analog or digital signals. So a signal whose amplitude can take any value in a continuous range is called an analog signal. This means that an analog signal amplitude can take an infinite number of values. A digital signal, on the other hand, is one whose amplitude can take only a finite number of values. So on the left here is an example of an analog signal. So as you can see, the signal amplitude can take any value here. But on the right we have a digital signal whose amplitude can only be -1 and 1. Two values. Two possible values to be exact. So analog signals can have an infinite possible signal amplitudes, whereas a digital signal has only a finite number of possible values. However, we must not mix up between analog and digital signals and continuous time and discrete time signals. These are two separate classifications. The term continuous time and discrete time qualify the nature of the signal along the time axis or the horizontal axis. So in order to determine if a signal is continuous time or discrete time, we need to look into the time or horizontal axis. The terms analog and digital, on the other hand, qualify the nature of the signal amplitude in the vertical axis or in the y-axis. So in order to determine if a signal is analog or digital, we need to look into the vertical axis. So a signal can be analog or digital and continuous time or discrete time at the same time. There is no clash. So here, for example, this signal is a continuous time signal because it's defined for the continuous value of the independent variable. But this is also an analog signal because the amplitude can take any value from -infinity to +infinity. This signal, on the other hand, is still a continuous time signal. This is a continuous time signal because it is defined for all values of t, not only for discrete values of t. But this can take only finite number of values, 1 and -1, 1 and -1. This signal is, for instance, is a discrete time signal and analog signal. And this signal is a discrete time digital signal. So all four combinations are possible. This signal is continuous time and analog. This signal is continuous time and digital. This signal is analog in discrete time, and this signal is digital and discrete time. So it doesn't mean that a signal is analog or digital and it cannot be continuous time or discrete time. Everything remains open. Now we're going to ask, how do we measure the size or strength of a signal? So in order to measure the size or strength of a signal, we use two parameters, energy or power. So energy is basically this, for a continuous time signal, is basically the integral of the square of the amplitudes of the signal, that is E equals to x squared dt. And for a complex signal, we take the modulus of the complex signal and then square it to obtain the energy. And these two are the equations for power of a real signal and a complex signal. Note that power is computed over a cycle, whereas energy is computed from minus infinity to plus infinity. Now you might be wondering how on earth a signal can be complex. It should be real. Well, it is often easier and efficient to express multiple signals as a complex number in various practical applications, such as modulation of signals in telecommunication and also in Fourier transform. If a Fourier transform a signal, the output you get is a complex number. Okay, now we're going to see another classification of signal, power signal or energy signal. So if a signal has finite energy, then the signal is called energy signal. So this is the example of an energy signal. So if you compute the energy of the signal, it will be a finite number. But if we apply the formula of power that we just saw and compute the power of this signal, of a signal which has finite energy, we see that the power becomes 0. So the power of an energy signal is always 0. So this is a property of an energy signal, that its power is always 0. Now if E equals to infinity, we cannot determine the strength of the signal by computing energy anymore, because energy is infinity. Instead, we do it by computing the power. So if for a signal the power is finite, then the signal is called a power signal. So for power signals, power is finite, but energy is infinite. So x of t equal to constant is an example of a power signal. So you can verify it for yourself. So please pause this video and try to find the power and energy of the signal x of t equals to 4 and comment if it is a power signal or an energy signal. So hopefully you've been able to do this. X of t equal to 4 is a power signal. Okay, now find the power and energy of x of t equals to t. Now please pause the video and then we'll talk about it. Okay, so I hope you found that the energy is infinity and the power is also infinity. So what do we do about it? So this brings us to an important idea. For some signal, energy is infinity and power is also infinity. So these are neither power signals nor energy signals. So x of t equals to t, which is also known as a ramp function, is neither a power signal nor an energy signal. So energy signals, in short, energy signals have finite energy but 0 power. Power signals have finite power but infinite energy. Some signals are neither power signal nor energy signals. It's not a binary option. So there are signals that are neither power signal nor energy signal, since both power and energy are infinite for these signals. Okay, now please pause this video and try to solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to do this. So the energy of this signal is finite, so it's an energy signal, and the energy of a cos omega t plus theta is infinity, which means the power is, and then we compute the power and we see that the power is a squared by 2, which is a finite quantity. So this is, we say that this is a power signal. Usually all periodic signals are generally power signals. So cos omega t plus theta basically goes from minus infinity to plus infinity, so the energy is infinity. Now we might ask, what is a periodic signal in the first place? Now we're going to talk about it. So signals can be classified in an additional category called periodic or aperiodic signal. So periodic signal is a signal that repeats itself every t seconds. So mathematically speaking, a signal x of t is said to be periodic for some positive constant capital T, where x of t equals to x of t plus x of nt, where n is an integer and t is the period of the signal. So here's an example of a periodic signal. So this pattern here, this triangle shape, this sawtooth shape, and this 0 gets repeated from minus infinity to plus infinity. There is no break. And this is a signal of an aperiodic signal. So this is basically a rectangular pulse that only exists between 0 to 1, and beyond 1 and below 0, the function is 0, and the pattern here, you know, this rectangular pulse pattern, does not repeat left and right, which is why it's an aperiodic signal. So the smallest value of t that satisfies the above periodicity condition is the fundamental period. And if a signal is not periodic, such as this one, it's called an aperiodic signal. So by definition, a periodic signal x of t remains unchanged if we shift it left or right. So for this reason, a periodic signal must start from minus infinity. So if it started at a finite time instant, let's say at t equals to 0, and if we shift it at left or right, then the signal changes. So it would not remain equal to the original signal anymore. Which is why if you shift a periodic signal left or right, you get the exact same signal. Therefore, a periodic signal by definition must start at minus infinity and continue forever, that is till plus infinity, as illustrated in this figure. So a periodic signal must always start from minus infinity and must always end at plus infinity. Another interesting thing about periodic signal, here we're just discussing how to visualize periodic signals here, because we cannot possibly draw a signal from minus infinity to plus infinity. So a periodic signal can also be generated by periodic extension of any segment of x of t, that is the original signal here, of duration t naught, where t naught is the period. So as a result, we can generate x of t from any segment of x of t having a duration of one period, that is capital T naught, by placing the segment and the reproduction thereof end to end from minus infinity to up to minus infinity and up to plus infinity. So what do I mean by that? So I mean, if I take the shaded region here from minus 1 to 5 and copy on the right and keep copying up to plus infinity, and then keep copying on the left, copy up to minus infinity, then we get a signal from minus infinity to plus infinity containing the copies of the exact same thing, this pattern from minus 1 to 5 seconds. And there you go, we've created our periodic signal. And it doesn't have to be this pattern, it could be any capital T. So the period of this signal is 6 seconds. So I could take any 6 seconds to generate this periodic signal. So in the bottom panel here, you see that I have taken a different 6 seconds. It is also acceptable. So I just copy this 6 seconds and paste it on the right side of this pattern up to infinity, plus infinity, and up in the left side of this pattern up to minus infinity. Once we do it, we get the periodic signal. So if a signal is periodic with period 6 seconds, we don't have to copy like a particular thing. We can copy any 6 seconds and paste it to the right up to infinity and paste it to the left up to minus infinity to generate the periodic signal. So that's the point here I'm trying to discuss. Okay, here is another classification of signal: causal, non-causal, and anti-causal. So a signal that does not start before t equals to 0, that is on the left of y-axis, is called a causal signal. So for a causal signal, x of t equals to 0 for t less than 0. So here I've shown a causal signal here. So on the left of the y-axis, you have the signal is 0, and the signal exists basically on the right of the y-axis. So x of t equals to 0 for t less than 0 in this panel, which is why this signal is a causal signal. A signal that starts from before t equals to 0 is called a non-causal signal. So non-causal signal exists both on both sides of the y-axis. So x of t not equals to 0 for t less than 0. So this is an illustration of this is an example of a non-causal signal. So this signal exists on both sides of the y-axis, as opposed to the causal signal, which only exists on the right side of the y-axis. There's another type of signal called anti-causal signal. For anti-causal signal, the signal is 0 for t greater than 0. So if you basically reflect a causal signal, you end up having an anti-causal signal. So the middle panel here is an example of an anti-causal signal where the signal exists completely on the left side of the y-axis, which is why x of t equals to 0 for t greater than 0. So the signal completely resides on the left side of the y-axis. So I'm going to talk about one last classification of signal: deterministic or stochastic signal, or random signal, versus deterministic signal and stochastic or random signal. So what is a deterministic signal? So deterministic signal is a signal whose physical description is completely known by us. It could be either a mathematical equation of the signal, or it could be a graphical form, but we know. So in short, a deterministic signal is a signal that can be expressed using a mathematical equation. When you cannot express a signal using a mathematical equation, it is called a stochastic signal or random signal. Most of the real world signals are stochastic signals or random signals, where we don't know in advance what the amplitudes of the signal is, what the frequency of the signal is, and what the phase of the signal is. We know nothing about the signal. So deterministic signal can be expressed by equation and whose frequency is probably known. Frequency, amplitude, these parameters are known. And a stochastic signal is something whose frequency is unknown. So we probably only have some information about like mean value of the signal or mean squared value of the signal. So example of deterministic signal are sine wave, square wave, waves that can be expressed using mathematical equation. Whereas human spit signal or human brain signal or electroencephalogram, these are examples of stochastic or random signals. These signals cannot be expressed using a mathematical equation. That's why they're called stochastic or random signals. And the frequency of these signals are also not known in advance. So this concludes our basic overview of signals and systems. So please let me know if you have any question in the comment section, and thank you.